All right. Good morning, everyone. Welcome back. Hopefully we have had time to register for my math lab. Remember, if you haven't, then you will be withdrawn/deleted from this course. All that paperwork is going to be turned in later today. So please make sure that you follow the rules for your courses. You don't want to get let out for silly things like that will only take 5 minutes. We are going to finish up 1.2 today, as well as begin 1.3. We're not going to get very far in 1.3. It's a long section. Most of the sections have got a decent amount of length to them in this course. And on average, each section takes about a day to complete, but that's on average, not any kind of guarantee. Remember, there is no homework for 1.1, even though we covered it very lightly. You have that chapter P homework you can do for 5 bonus points on the first test. That will be due the day before the first test. And these things will be put on the whiteboard eventually. And since we'll be finishing 1.2 today, it will be due in 1 week. So that would be, what is that, the 25th? Yes, the 25th. And again, I'll have this written up. But again, anytime we finish a section, if I don't write the due date on the whiteboard or say it out loud, it is an assumption because these are in the rules of the syllabus. Homework is always due 1 week later. All right, and thank you for letting me know about that private message. So let's just show the list of instructions we had last time. And again, if you miss anything, you can. I always, for these recorded sessions, I always go back and put them on YouTube. If and when we go back to live in person, then these will not be recorded anymore. You'd have to get notes from someone else. Which, by the way, in case you missed the email from TCC, this is the MDE notes. Hold on, I've got the wrong thing pulled up. There we go. In case you missed the email or announcement from TCC, we are going to be continuing Zoom, obviously, today, but throughout January. So February 1st is supposed to be the first day back in classrooms. Of course, this is still tentative. This is still based on how Omicron wave is going. So keep your eyes and ears peeled. I will, of course, let you know any changes to the schedule. But for now, the next 2 weeks or so, we'll be continuing on Zoom. And it is what it is. All right, so refresher on 1.2's instructions for linear and rational equations solving. So this is a pretty good recipe. First thing, if you see any distributions or combining of like terms that you can do it. Then, if you see any fractions in your equation, remember equations, the trick to something being an equation is that it has to have this equal sign built into it. If there's no equals, it's not an equation, it's an expression. And this trick doesn't work. You can't get rid of fractions or decimals in expressions, just equations. Has to be a left and a right side to it. So you find your LCD and you multiply everything by the LCD, and that'll get rid of your fractions. The same is true of decimals, as we'll see in our first example today. If you see decimals, it's still an LCD, believe it or not, because decimals are fractions. In fact, the official name of decimals is decimal fractions, just nobody calls them that because it sounds kind of geeky. So with decimals, if you have a 0.1 and a 0.5 and a 0.02, you just want to say, well, how many decimal places do we have at most? Well, that would be 1, 1, and 2 for the example I gave. So 2 would be the most. And then that's how many zeros you need in your multiplier for a power of 10. So 10, 100, 1,000, you'd need to multiply by 100. Because when you multiply by a power of 10, you just move each decimal right by the number of zeros. So by counting the maximum number of decimal places, you'll make sure you have just enough zeros to move all of the decimals right enough to make everything a whole number. Could you multiply by a bigger number? Sure. If you need to multiply by 100, you can multiply by 1,000. You can multiply by 1,000,000. You can multiply by 1,000,000,000. It'll get the job done. But then you're going to have bigger, hairier, squirrelier numbers to deal with along the way. So yes, common denominators always work, but these common denominators are the best. Once your decimals and fractions are gone, you move things from side to side by adding and subtracting, working in opposites. That's how we move things in equations from one side to the other. We work in opposite operations. So if you see an addition, you subtract. If you see subtraction, you add. You want to get the variables on one side, the constants on the other. You want to isolate them. You want to quarantine them, as it were. And then you should end up with something like 5x equals -41, like this point in A, and you just divide both sides by the coefficient of x. Now, not all of these steps have to happen. We saw examples where 1 wasn't there. We saw examples where 2 wasn't there. We might see an example where step 4 doesn't happen. It's all a possibility. I also mentioned that these 4 steps, the order is technically arbitrary, especially steps 1 and 2, but this is just a best practices order. This is generally the easiest way to get things done. But note that sometimes for crazier problems, step 1 might creep up later. Step 3 might creep up later. And we did A, B, and C. We had 2 examples with fractions. Go back and check those videos out if you missed them. And what we're going to start with today is D. And I usually just kind of keep my notes all on the same page, but I'm going to try something different this semester, divided up by week. So for D, and we're still solving, we're going to have 0.2x minus 0.42 is equal to 0.5. All right. Cursor out of the way. It's annoying me. And this is 1.2 continued, by the way, in case you missed that. This is 1.2 continued. So we're solving this. I don't see any distributions. I don't see any like terms. Oh, but Mr. Beckner, 0.2 is like 0.5. They're not on the same side. So sure, if you want to go ahead and move things, if you want to do step 3, if you want to move the 0.4 to the other side by adding, go for it. That's fine. But then you got to add decimals. That might annoy you. I'd rather just get rid of the decimals. So we're going to find the LCD. But Mr. Beckner, LCDs are for fractions. Ah, but student, decimals are fractions. Because this 0.2 is like 2/10. This 0.42 is like 42/100. This 0.5 is like 5/10. If you would prefer to change that and deal with your LCDs that way, be my guest. That's fine. Nobody cares. You might say, well, reduce your fractions first. Sure, could, but that actually might make it worse. Not impossible, but worse. So we have 1 decimal place here, 2 decimal places here, 1 or 2, I was about to say that wrong, and then 1 decimal place here. The most decimal places I saw was the 2 from the 0.42, and you can see that 2 decimal places several times. It doesn't have to be just once. So our LCD is 100, not 1,000. I don't need 3 zeros. I'm not going to say, oh, 1, 2, 3, or 1, 2, 3, 4 decimals, so 10,000. You're just taking the most. This is where the most was from. So we're going to multiply 100 by the 0.2x. We're going to multiply 100 by the 0.42x. And we're going to multiply 100 by the 0.5. Be careful with the way you're writing this. Make sure your decimals are lower than your multipliers. You don't want to think of decimals a dot multiplier. And then all that does is just moves each decimal right twice. So for this 0.2, you might want to write it to the side, 0.2, when it goes right twice. There'll be a filler 0 here, so that becomes a 20. For the 0.42, and when it goes right twice, that's going to make it a 42. And for the 0.5, when it goes right twice, there'll be another filler 0, and it becomes a 50. So this becomes 20x minus 42 equals 50. Boom. No more decimals, no more fractions, much easier on our brains. And from here, we're at step 3 in those instructions, which was to move things from side to side in order to isolate the variables, in order to quarantine the variable, in order to quarantine the constants. Maybe one of them's got omni and the other doesn't. The only x's on the left, so let's not move them. We have constants on both sides, so let's move one of them. Since the x's are on the left, it would be quickest to move the constants to the right. So we want the 42 to go right. And we do that since it's a minus, we add 42 to both sides, giving us 20x is equal to 92. Final step, step 4. That is a multiplication of x. To undo multiplications, we divide. We do not subtract. You might say, oh, that's a plus 20, so subtract 20. No, because that's 20 times x. Subtracting 20 would not unravel it. You divide both sides by 20. And when you divide, you don't divide by the x. Those 20s will cancel each other out on the left and give us, I'm just going to write it over here, x equals 92 divided by 20 does not divide perfectly, but it does reduce. You could say 2 goes into each of those, but you'd have to do it again. If you want to get this done quicker, you can say 4 goes into both of these. 4 will go into 92. Let's see, 80 would be 20 of them. There's 12 left over, so another 3, so 23 in the top. 4 will go into 25 times. 23 over 5 is a perfectly acceptable answer. Or if you want to convert that to a mixed number, 5 goes into 23 4 times with the remainder of 3. Or if you want to convert it to a decimal, that would be 4.6. Now, I have the 23/5 boxed up because in my opinion, that's the best answer. It's the easiest answer. It's the least work, and you won't make a mistake converting it. So that would be the way I would do things. My math lab generally accepts improper fractions as answers. It will let you know if it does not, whether it's homework or test. And if it's a test, I generally am not going to care what format it's in, unless that was the entire point of the problem, which in pre-calc, that's really not going to be the case. So don't take the extra time to convert things. And remember, you are not allowed calculators for your first 2 tests in here, so you need to be capable of reducing your fractions and handling this basic level arithmetic. Answering your question in chat. Felt like I should type that one. Okay. So, could we have done 20, 30 of these? Yes, if we had time, if this was a lower level math class, but we have to move forward. We're going to go into what we call the 3 different types of solutions, and they are known as conditional, definition for it, inconsistence. I got my degree in math, not spelling. So these are the 3 types of solutions. A conditional solution means that a solution or several solutions. In other words, you found something like x is equal to a number. An identity means that sides of the equation exactly an inconsistent solution means a false statement. Everything that we have done so far, example 1, A through D, has been conditional because we found a solution. In particular, those solutions were for A, -41/5, for B, -4/13, for C, -14, and for D, as you can see, 23/5. Those were conditional. That means 1 or 2 or 3 or 4 or 5 solutions were found. You might say, oh, you can only have 1 solution. Not true. You can have 2 or 3. We get to factoring, we get to quadratic formulas, etc., etc. What we haven't seen so far is an identity or an inconsistent. Spoiler alerts for what's coming up. So an identity means both sides of the equation match exactly at some point. What the heck does that mean? Well, it means exactly what it says. The left side will be exactly the same thing as the right side. An inconsistent is going to feel like an identity. It's going to look like part of it's the same, but then there's one little detail that's off. A false statement is found. Now, some students will be able to see that inconsistent when the sides are not quite matching. But what I generally say is just keep trying to finish the solving process, and it becomes very obvious that it's inconsistent. And we'll show you what we mean. All right, some extra little details. Identities have infinitely many solutions. And you might see this written in a fancier way. It'll look like this: X, where X all real. That's a fancy way of saying it. Sometimes you might see a symbol for this, which is a double back R. that looks like one R. It's kind of a bad. There we go. That's a double back R. That's the symbol for all real numbers. This is in set builder notation. This is the symbol for all real numbers. Usually in my math lab, you're going to see it this way, the way I have it highlighted. Inconsistence inconsistent have no solution. And so we have this in those little curly brackets. Is a 0 with a line through it like that. That means the empty set. It means the null set. It means nothing. You get nothing. Good day, sir. Sorry, I know I have silly references. So identities means that every number you can imagine in the real world, in the real number system, is a solution. 5, 3, 2/5, 0.1, pi. They all work. Inconsistent equations means nothing works. There's no number you can imagine that would solve the equation. So for example, 2. Well, that was the same instructions as example 1. Must be the same thing, right? Well, 4x plus 5 equals 4x plus 5. But on one side, there's a parenthesis. Oh, that looks like they're both the same thing. It must be an identity. Or, oh, they don't look the same. So it's well, don't try and jump to conclusions yet. When you think you have an identity or an inconsistent, don't even worry about it yet initially. Just try and solve this thing. Do exactly what you did in example 1. Don't worry about all this stuff we just said. Just solve it. Do what the instructions say. And eventually it will become clear that it's an identity or an inconsistent, or conditional if they were, but spoilers not. All right, so the first thing we can do is distribute. And when we do that, we're going to get 4x plus 5 equals 4x plus 20. Some students will already know what's happening here, but again, I'm going to pretend like I'm not that student. Keep the solving process going. So you go, all right, well, there's no fractions or decimals, no LCD stuff. Move the variables to one side, constants to the other. So we have 4x on the left, 4x on the right. Well, that's interesting. We have just as many x's on both sides. We haven't seen that happen. Well, let's just say we want to move the ones on the right to the left. That's a positive 4x. So I'm going to subtract 4x on both sides. Coincidentally, if you said you wanted to move the ones from the left to the right, you'd do the same thing. Now, I said I'm moving my x's left, so I'm going to move the constants right. So I'm going to say I'm moving the 5 right, so let's subtract 5 on both sides. And when I do this, the 4x's cancel, the 5's cancel, and we get 0, equals, the 4x's cancel, 20 minus 5 is 15. Wait a minute. Mr. Beckner, all the x's disappeared. That's kind of strange. That's a little weird, right? Yes, exactly. This is your red flag that you either have an identity or you have an inconsistent. When your x's disappear, maybe write this down. I'm going to say it very sternly. When your x's disappear, it's an identity or it's an inconsistent unless you made a mistake somewhere. Now, did I actually have to move the 5 and the 20? No. Check this out. If I didn't move the 5, I would have just brought the 5 down. And I would have brought the 20 down. And I would actually get the same conclusion. Before I had 0 equals 15, now I have 5 equals 20. Well, that's not the same conclusion, Mr. Beckner. It's just a different number equal to a different number. But what we have is a false statement. 0 is not 15, 5 is not 20. If you have different numbers on the opposite sides and the variables are gone, that means you have an inconsistent equation because you have a lie, you have a false statement. This is false. False means there is no solution. It means If you wanted it in the set builder notation, it would look like that. Those are both great ways to represent no solution. Because we have a lie. The x's are gone, and we have a false statement. For B, this one's going to look very, 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 very similar, except I'm going to go 4x plus 20 equals 4 parentheses x plus 5. Okay. Well, the first step feels the same, distribute. I'm not even going to write it. It's clearly distribute 4x plus 20 plus 4x plus 20. Now, again, some students may recognize the ultimate answer here, but I'm going to pretend like I'm not that student, and I'm going to keep going. So I'm going to say, all right, Mr. Beckner wants us to move the x's around. So let's subtract 4x on both sides. Exact same step as last time. Oh, I forgot to rewrite this part in. I subtracted the 5 on both sides. Here we go. Now this time I'm going to choose not to move the constant. Since I did it last time, I'm not going to do it this time. I want to break this down in 2 steps instead of 1. The 4x cancels on the left, the 4x cancels on the right. Now what a lot of students like to do is say, well, that can't be, so I'm going to leave an x on one side. Well, that would be weird. Why would 4x minus 4x be nothing on one side and be x on the other side? So the 20 is left on the left side. The 20 is left on the right side. Now, sure, I could subtract 20 on both sides if I wanted and get 0 equals 0, but the variables have disappeared, which is already our red flag that it's either nothing or everything. And it's all about whether you get a true or a false statement. And this is a true statement. True statements are when you have exactly a match on both sides. They match exactly. That means it's a true statement. And in fact, 4x plus 20 was the same thing as 4x plus 20. You could have made the conclusion up there. I just tend to like students to wait until the variables disappear. True statements means that everything is a solution. So you could write that double back R. You could write curly bracket X where X is real. Or you could write all real numbers. All 3 of those are valid solutions, and I believe my math lab does the middle way. In other words, pick a number. Pick any number you want in the world that's real. 3, 9, negative a million. If you plug it into the x here and the x here, both sides of the equation will match. I'll just do a 2. 4 times 2 is 8. 8 plus 20 is 28. So that's the magic number. All right, plug the 2 in where here. 2 plus 5 is 7. 7 times 4 is 28. It works. Remember, a solution makes the left side match the right side, but with no x's up here, the left side already matches the right side, so the variable is independent of the solution. So those are kind of cool. Right. Let's get out of the linear world and let's go to the rational equations. So I'm going to give you a recipe to solve these, just like I gave you a recipe for the linear equations. And it's actually not that different. It's basically just 1 or 2 extra steps. Well, that's not really entirely true. First off, you're going to factor the denominators. Denominator means bottoms. You can factor the tops if you want to, but it's really not going to do anything for you for this process. So if you don't remember to just factor the denominators, factor everything. It won't hurt you. Then identify LCD. Multiply all terms, all rationals. That is spelled correctly. That's an appropriate term. Sometimes Word just doesn't like math words. Identify your LCD and multiply all terms. That's the same step as step 2 from before. Rational means fraction. We talked about that last class. Rational means fraction. When we have rational equations, we're not just meaning equations like x over 5 or 3x plus 2 over 7. We're talking about things like x plus 2 over x minus 9. Variables littered all over the place. Well, the thing is, since rationals are fractions, you treat them the same way. You find your LCD and you get rid of the fractions. So that's convenient. It's just the LCD is going to involve things like x plus 2 and x minus 7. All previous so move things from side to side, combine like terms, distribute, divide by the number in front of the x at the end, etc. Oh, sweet. So we're done, right? Well, the problem with rational equations, the problem with having variables in the bottom is that sometimes you get what's known as, and this is a fancy term, an extraneous solution. It's a solution that you get in the process, but it doesn't actually work. And that kind of feels like real life. Hey, I've got $40,000 worth of bills. How do I pay these bills? Well, I could go rob a bank. That's an extraneous solution. It seems like in the short that it's going to work out for you, but in the long, you're going to jail, right? Probably. So it's a solution you come up with that seems to work, but in reality, it doesn't. That's an extraneous solution. Why is this? Because when you have x's littered in the bottom, what if you had a number that made that bottom 0? What's the one number in the world we're not allowed to divide by? 0. So what if your solution just happens to also make the bottom 0? Well, that's a problem. And you know what you do with the solution? You throw it away. So we have to check solution. Easiest way is not actually to plug in the solution and see if the left side matches the right side. It's to plug it into the LCD. Makes it the solution. LCD 0. Why exactly does this work? The LCD encompasses all possible denominators. So if your solution makes the LCD 0, it means it makes one of the denominators 0, which means you're dividing by 0 somewhere and the world explodes. The problem is step 2. The problem is when you multiply all the terms and rationals by your LCD, you're ignoring that temporarily. You're saying, get rid of the denominators, which is fine for the solving process, but it is still an important detail of the equation that might cause problems. Now, this wasn't a problem in the previous examples we saw because there were no variables in the bottom. There was no way the bottoms could have ever been 0 because they were things like, I gotta pull my examples up, 4 and 3. But now we're gonna have an x in the bottom, which means maybe the bottom could be 0. And we will see an example when this happens, of course. Now, when you get to checking your solutions, maybe you forget this, maybe you just plug it the left side and the right side in and see if they match. Okay, that's fine. It's gonna be more work though, trust me. Also, trust me, if you forget to check your solutions, you're gonna miss probably more than half of these in your homework and your test, because we love to give ones where a solution doesn't work. Now, step 1, factor the denominators. I'm actually not supposed to introduce the factoring techniques until another section. So you might see me do something in one problem that you don't quite understand. Again, this is technically prerequisite material. This is stuff that you can go back to my math lab assignment. You can go to the Canvas notes that I gave you. I will give a very, very ridiculously quick introduction to factoring in the next 2 classes. But for now, I am just going to do one problem where I factor something and kind of assume you already know how to factor. But again, that's really how it's supposed to be in this course. I'm being very, very nice in the next day or 2 by giving a quick review of factoring. All right, example 3. Y1, and I'm going to do this because of my math lab homeworks and tests. 3 over x plus 6, then plus 1 over x minus 2. And then we'll have y2 is equal to 4 over Where's that? X squared plus 4x minus 12. Yep. And we're going to say solve y1 equals y2. You will see homework problems like this. You might see, you will probably see, that's me whispering, hopefully not too creepy. You will probably see something like this on a test. This is not anything crazier than anything we've just done except the fact that they're rationals. All it means is by saying solve y1 equals y2, we're going to set this jazz equal to this jazz. That's all we're doing. I've given you an equation implicitly to solve. So what we're really doing here is solving 3 over x plus 6 and plus 1 over x minus 2 equals 4 over x squared plus 4x minus 12. Again, by me giving you this, this is what you should set up. All right. X plus 6 is not factorable. X minus 2 is not factorable. Why? Because I don't see any x squareds and I don't see any GCFs or x cubes or x to the fourth or x to the fifth. Greatest common factor, that's when I might have like a 2x plus 6. I could take a 2 out of both of those. Or an x squared plus 6x, I could take an x out of both of those. Again, I'll give a super quick review soon of that, but for now, it's implicit information. However, this x squared plus 4x minus 12 is factorable. That's what we call a trinomial with a leading coefficient of 1. We'll get into more detail about that later. So let's factor. I'm just going to do this to the side. X squared plus 4x minus 12. Now, there are about a dozen different ways you could have been taught to do this. I don't care how you factor as long as you can get the job done. The way I teach my developmental students, or hold on, the way I previously taught my developmental students, we don't do developmental anymore. It's my direct enrollment students, is I take the number at the end, the minus 12. So I'm going to take this minus 12, and I'm going to write all the multiples of it in pairs. 1 times 12, 2 times 6, and 3 times 4. And again, I will be writing these instructions down at a later date, and then I'm going to figure out which of these pairs will subtract, since that's a negative, to make this number, this positive 4. Well, 12 minus 1 is 11, so that doesn't work. 4 minus 3 is 1, so that doesn't work. But if I do 6 minus 2, that does work. And then I need to give these signs to make sure they come out to a positive 4, because do I do 6 minus 2 or do I do 2 minus 6? 6 minus 2 is positive 4, 2 minus 6 is negative 4. I want a positive 4, so it's a minus 2 and a positive 6. These are the numbers that will go over here. This form with a leading coefficient of 1 is always x number, where the numbers are right here, the minus 2 and a plus 6. But you have to have signs with them. And if you don't trust this, you can FOIL to check. FOIL, first, outer, inner, last. X times x is x squared. The outer and the inner would be a positive 6x. The inner would be a negative 2x. 6x minus 2x is 4x. And the last, negative 2 times 6 is negative 12. Again, I know some of you, your heads might feel like they're exploding right now. If you've never seen this before, that's terrifying, and you've got a lot of work to catch up on, because factoring will never go away in pre-calculus or calculus. And that's the downside of direct enrollment. And if you're in my MDE class, we'll be doing more practice with that stuff, a lot more practice than in here, because we barely practice in here except inside of examples. But this is a constant issue in here. All right, so now we go back to the original problem. We had our 3 over x plus 6 plus 1 over x minus 2 equals to 4 over, the factored form is x minus 2 times x plus 6. Mr. Beckner, could I write x plus 6 and then x minus 2? Yes, you can, Bob or Jane, or whatever your name is. That was me asking a question to myself. So we got step 1 done. We factored. Now we're at step 2. Identify your LCD and multiply all terms by it. This isn't like our LCD. We have denominators of 3 and 4 is 12. We have denominators of x plus 6. We have an x plus 6 here and here. And we have an x minus 2. We have an x minus 2 here and here. Now, the cool thing about repeated factors is they don't need to be repeated unless any of them have exponents with them. So if I had an x plus 6 squared, I'd need an x plus 6 squared in the LCD. But I only need the x plus 6 a single time, and I only need the x minus 2 a single time, because when I multiply that out in each fraction, I only need to cancel one of them each time. Now, in this type of example, if you do have extra things in your LCD, if you have an x plus 6 squared and an x minus 2 cubed, you will create a disaster equation that you probably won't be able to solve with your available techniques. Is it solvable? Yes. Is it going to be nearly impossible for you? Yes. Will you get more extraneous solutions? Possibly, in fact. Okay. So what do? Multiply all terms or rationals by it. Even if any of these things were not fractions, if this was just a 4, I would still multiply the entire LCD by it. So I'm going to show the LCD after the fraction part just because it looks goofier otherwise. And I'll do these as they come along. So the first fraction gets it. The second fraction gets it, even if it wasn't a fraction. And the third one gets it. Holy cow, that got way uglier. That got terrifying looking. Mr. Beckner, what are you doing to us? Why do you hate us? I don't hate you. I love you. We're doing this for a reason, and the reason is it's going to make things simpler. So these do get uglier temporarily, just like the fraction equations got a little uglier temporarily. But again, the point is, this is still a fraction equation. The point is to get rid of the fractions. Check it. Checkity check it. X plus 6 in the first fraction. There's one top and bottom gone. Don't cancel something from this fraction to this one. Do not, I'm going to highlight, do not try and cancel this x minus 2 with that x minus 2 because of this plus sign. You can't do that. If it was a times you could, but it's not, so don't. X minus 2, gone. First thing is no longer a fraction. The second thing is no longer a fraction. This third thing, the x plus 6s are gone, the x minus 2s are gone. It's only the 4 that's left. It is insane how much this cleans up. 3, parentheses, x minus 2, plus. Do I really need to write the 1? No, but I don't want to confuse you. 1 times x plus 6 equals 4. No more fractions. Hallelujah. Praise the math gods. Or the math devils, whatever you want to praise. Whatever math religion you're in. We don't discriminate here. Okay, so now just do whatever you got to do in that solving process. Distribute, combine like terms, move things from side to side. In particular, we can distribute. We distribute the 3, we'll get 3x minus 6. If you distribute the 1, not a lot's going to change. It's x plus 6, and then equals 4. Combine like terms. CLT, combine like terms. 3x plus x is 3x squared, right? If I do 3x plus x, that's x, I'm sorry, 3x squared, right? Wrong, no. Remember, variables that don't have numbers in front of them, you assume there's a 1 in front of them. Nobody ever writes that 1. So 3x plus 1x is 4x. Negative 6 plus 6 is actually 0. They cancel each other out. So we get 4x equals 4. And then divide. Divide by what? The number with the x. 4x divided by 4 gives us x equals 1. Now, I'm not going to box this up yet. I am not doing this yet. I'm not doing this yet. I'm not doing that yet. See, I undid it. You might go, why not, Mr. Vector? We got the answer. We're done. Type it in. This is a maybe for now. The one thing that will get you, and you're really going to be kicking yourself if you take a test and you make it this far and then it doesn't give you any points because it says you're wrong. If that were the case here, maybe it is, maybe it isn't. It's because you forgot to, step 4, check your solutions. You have to check your solutions. And we said the easiest way to do that was to plug this into the LCD and see if it makes it 0. For the checking, I'll do that up here. You take your x equals 1 and you plug it into the LCD. The LCD being the x plus 6 times x minus 2. So our LCD becomes 1 plus 6 times 1 minus 2, which is 7 times negative 1, which is negative 7. Now there is one number and only one number we don't want this to be. We don't want this to be 0. Well, this is not 0. That's the not symbol. So that means it's okay. It's cool. It's fine. The solution does not make the x plus 6 0. The solution does not make x minus 2 0. So it won't make the x minus 2 times the x plus 6 0 either. So none of the denominators are 0. The world doesn't explode. So that means that we can definitively say x equals 1 is the solution. Now you might say, oh, well, sweet. It worked on a test. I can just skip the checking and I'm okay. Flip a coin and maybe you're okay, maybe you're not. Maybe it's heads, maybe it's tails. And it's about 50% of the time, maybe a little more than 50% of the time that it doesn't work. I used to be really cruel and I always gave problems way back in the day that none of the solutions would ever work or all but one would work. And the students would go, oh, well, I'm just gonna be clever and I'm writing no solution no matter what. And I go, well, if you don't show your work, you're not getting any credit. I still could do that, but I don't. Well, Mr. Beckner, you said you'd give us one where it doesn't work. Spoilers, geez, why you gotta ruin everything? One more, and we'll be done with this section. 5 over x plus 2 plus 3 over x minus 2 equals 12 over x squared minus 4. I'm always curious if y'all can hear my dog in the background. He makes all kinds of noises. All right. 5 over x plus 2 plus 3 over x minus 2 equals 12 over x squared minus 4. I'm going to scroll up to the instructions real quickly as a reminder. I hope you're taking notes. Factor the denominators if you can. If you got tops that are factorable, go for it, but it's not going to do anything for you. Find your LCD and multiply everything by it. Even if there's a part that's not a fraction, multiply it. Solve using the previous linear instructions. Check the solutions by doing that LCD stuff. There are many different ways you can check. This is just one of them. All right, so factoring the x squared minus 4. This is what we call a binomial. It's called a difference of squares. You'll get a formula for that later. It's a squared minus b squared equals a plus b times a minus b, which means this is x plus 2 times x minus 2. That's a formula you have to have memorized. You will see it constantly throughout this course. Again, I'll give that to you in our super quick review. You also will see it in those Canvas notes. I even pointed it out day 1. Hold on, give me 10 seconds. All right. So that's the factored form of that. So this is going to become 5 over x plus 2 plus 3 over x minus 2 equals 12 over x plus 2 times x minus 2. Now you might say, oh, well, you know what? I just noticed a pattern between the two examples you gave us. Both of these denominators ended up being the factored form. You know what? That's actually fairly common that at least one of these is in the factored form, and you can use that as a shortcut of your factoring methods if you like, kind of a precursor, if you will. Is it always going to be the case in the real world for every example, for every test problem? No, but it is pretty common because when you start having 3 and 4 and 5 unique factors in the bottoms, it starts making the equations much more difficult. All right, so the LCD. I only see a single x plus 2 in any individual denominator. I only see a single x minus 2 in any individual denominator. So I don't need 2 or 3 or 4 of those, just one of each. And then each piece will multiply by the LCD. Mr. Beckner, you didn't do this in the bottoms. Yeah, I didn't do it in the bottoms of the other fractions that were simpler either. Multiplying the left side and the right side by something means it's over a 1. You're not multiplying these top and bottom, you're multiplying the tops by them. And then cancel. In the first fraction, x plus 2's are gone. The second fraction, oops, wrong one. X minus 2's are gone. In the third one, the x plus 2's are gone and the x minus 2's are gone. Leaving us with just a 5 and then the x minus 2 in parentheses plus a 3, the x plus 2 in parentheses equals 12. It got really terrible looking for a minute, but it cleaned up nicely very quickly. Distribute. We'll get 5x minus 10, not equals, excuse me, I'm looking at something else, plus 3x plus 6 equals 12. Combine your like terms. 5x plus 3x is going to give us 8x. Negative 10 plus 6 is going to give us a minus 4 equals 12. Then we move things from side to side. There's only x's on the left, so let's not choose to move the x's. You can, but it's just going to waste time. There are constants on both sides. If you move the 12 left, everything's going to be on the same side. You don't want to do that, so add 4 to both sides. Sure, you can subtract 12 on both sides. Sure, you can subtract 8x on both sides. That's not really going to benefit you, except to take longer. 8x is left alone. The 4's cancel, equals 12 plus 4 is 16. Our last step is to divide. Divide by what? Positive 8. And that will give us 8 divided by 8 is 1, so that's just x equals 16 divided by 8 is 2. And if you box it up, nope, you're not supposed to box it up yet because we're supposed to check your solutions. Let's do the checking over here. Remember, we're taking the x equals 2 and you're plugging it in to the LCD. There's only one number we don't want this to be, and that is 0. So our LCD, earlier we said was this x plus 2 times x minus 2. So that becomes 2 plus 2 times 2 minus 2. Where did these 2's come from? Because we're plugging in the x. The x's become 2's. 2 plus 2 is 4. 2 minus 2 is 0. 4 times 0 is 0. Uh-oh. That was the one number we don't want it to be. We don't want the LCD to be 0. Because if the LCD is 0, that means by plugging in that 2 somewhere into a denominator, one of them's 0. In particular, if you plug in 2 here, 2 minus 2 is 0, 3 divided by 0, world explodes. If you plug it into this denominator, that becomes 2 plus 2, which is 4. This is 2 minus 2, which is 0. 4 times 0 is 0. 12 divided by 0 is world explodes. So 2 of the 3 denominators become 0. You're breaking all the rules. It means the x equals 0, I'm sorry, x equals 2 doesn't work. It fails as a solution. It's extraneous. Fancy word. It's us. How do we make our $40,000 a year? We rob a bank. Extraneous. It sounds like it's going to work, but it doesn't because you're going to jail. So we're going to math jail if we say x equals 2 is the solution. We've just robbed a bank because actually it's worse. We've made the world explode. Now, it is possible with these to get multiple solutions. Maybe we found x equals 2 and x equals 3 were potential solutions. 2 would fail, 3 wouldn't, and we'd say the solution is x equals 3. But all the solutions we found, the single solution we found failed, which means there is no solution. Or that fancy 0 with a line through it. That can happen. So again, if you're really rusty with the factoring, you are going to need to spend independent time working on this. If you're in my MDE class, we will spend class time in there, but you are still going to be responsible for spending independent time working on this stuff. And I know probably half of you are rusty with factoring. It's just kind of the typical ratio. But it is assumed knowledge moving forward. Factoring will never go away. It's a part of us. It should be a part of us. What happened to my mouse? That was weird. So that is 1.2. We went over linear equations. We gave you a recipe to solve those. We went over the types of solutions, conditionals, identities, and inconsistents, which meant there are countable solutions, there are no solutions, or there are infinitely many solutions. We went over rational equations. We didn't give too many examples, but we did enough to move forward. And again, everything we've done so far has been technically review material. All of this was in MDE 60 or MDE 10. So we're going to move on to 1.3, and I actually have some of this stuff pre-typed. Models and applications. Sometimes I'll have things already set up. Sometimes I've got them. I'm going to write them on the fly. I just do a mix and match. Models and applications. You know what that means? Everybody's favorite. It means everybody's favorite. It means word problems. Oh boy, yay, word problems. If Bob is on a train going 60 miles an hour heading east and Jane is on a train going 65 miles an hour west, at what point do their heads explode? Lots of explosions in here. We're not going to do a ton of word problems in this course, admittedly, but we will see them intermittently. I don't give a ton of word problems on tests. You'll see maybe 2, maybe 3 on this first test. And then honestly, only like 1 on each test after that. So don't let this feel like the end all be all because you hate word problems. You're going to have to do the homework on them. You're going to see a couple on tests here and there, but it's not going to make you fail this course because you can't handle word problems. So how do we handle word problems? Well, you read the question, you read it again, you read it again. Soak in details a little bit at a time. Don't try and take in everything all at once because your head will. So read the question just to get an idea of what's happening. Then read it again, looking for the details, looking for the numbers. Start identifying things. Oh, Bob was going on that train 60 miles an hour. Write that down. Oh, Jane was going on the train 65 miles an hour west. Write that down. I didn't make this a solvable example. I just said some things to be silly. Write stuff down. Write details down. Identify what you know. Identify what you don't know. The things that you don't know, you're generally going to be labeling as variables. Now, with some word problems, maybe you only need one variable, just an X or an N or whatever letter you like. Crazier word problems, you might need X's and Y's, maybe X, Y's, and Z's. It just depends. Maybe you can label one thing X and the other thing like an X plus 5 because somewhere it says Bob is going 5 miles an hour quicker than Jane. So Jane would be X and Bob would be X plus 5. You would need a Y in that situation because I've related one of the unknowns to another unknown. And that's pretty typical for us. At some point in the problem, they should give you a clue or a direct statement of what the equation should be. Write that equation out in words, like your mommy and daddy told you as children, use your words. You know, maybe interest 1 plus interest 2 equals total interest. Or maybe plan A cost equals plan B cost. Or I don't want to spoil too much, for example, when person A plus person B plus person C equals total. Then what you want to do is take your knowns and unknown statements, take your equation statement and your words, and start mixing them together. Start throwing your numbers and your variables into the equation. So instead of writing Bob plus Jane equals 70, write X plus 5 equals 70. I never said 70 before, but I'm just giving you an example of what it might feel like. So that's where you're placing your knowns and unknowns into the equation you wrote down, which should be solvable. Excuse me. And when you solve that equation, because we're dealing with real world parameters, even though there might not have been rational equations, you still might need to check your solution. Especially when we're dealing with geometric problems in this course, it's possible that you get an extraneous solution just because it wouldn't make sense in the real world. For example, maybe I say, sorry, hold on. Hold on. Sorry, my dog was being weird. Okay, so maybe I say you've got two angles that add to 90 degrees, solve, and you come up with the first angle is, or sorry, let me say you've got a triangle, a right triangle, so one of them is 90 degrees, and I tell you to solve the angles. So you got a right triangle, and I want you to find the other two angles, and you find that the first angle is negative 12 degrees. Well, that wouldn't make sense because the interior angles of a triangle can't be negative, so you throw it out. Maybe you found multiple solutions, and that means you throw the negative 12 out, and the other one probably works. Or maybe it's just not a solvable equation. Maybe it was a lie to begin with. So you have to think in terms of real world context. Also, with our word problems, the answers generally make sense in the real world. Like, let's say I asked you to find the speed of a car, and you came up with 9,000 miles an hour. Well, that wouldn't make sense. You probably goofed somewhere. So one thing I teach my quantitative reasoning students is to always make sure their answers make sense. And in here, I'd like to think the same way. All right, so we will not finish this section as promised. We got about 15 minutes. We can knock out one or two examples though. So let's knock out an example or two. Try not to show that last little detail. So example one. Now with these word problems, when you look at the homework, you might say, oh, you didn't do an example like number 7. You did 1 through 6 and number 8, but not 7. But the point in here is not to do every single type of word problem for you. It's to give you enough types that you can then use your knowledge and skills to do things that maybe you haven't seen. All right, so out of 3 majors that colleges offer, and I will give you time to write this down as well. Out of 3 majors that colleges offer, psychology, business, and English, not saying these are all the majors that colleges offer, but that would be really weird. I wouldn't have even had a degree because I didn't study any of these things. I had a microeconomics class. I kind of wish I had taken business classes, but I do love my my applied math degree. The business major on average makes $8,000 more than the psychology major. Doesn't say always, it says on average. The English major makes on average $3,000 more than the psych major. So we're relating each of these to each other by saying one of these guys makes more than the other, one of these girls makes more than the other. These people makes more than the other. All inclusive. Okay, if the sum of these three majors averages, it's not saying starting salaries, it says average salaries. So don't think that the numbers we get at the end are going to be what you make right out of college. It's also a giant misconception. If the sum of these three majors averages is $116,000, what is each major's individual average? So we're trying to figure out what is the average English major salary? What is the average business major salary? What is the average psychology major salary? Give you about another 90 seconds to write that down. While I take a water break. Okay, so first read the question, read it again. Hopefully you're going to do that on your own time. Hopefully you've had time to do it now. Identify your knowns and unknowns, give the unknowns variables. So what do we know? We've got three majors: psychology, business, and English. Shoot, I didn't want that. Yep, psychology, business, and we have our. Let's write down what these salaries are. Well, the psychology major makes $20,000, right? No, I didn't say that anywhere. What did we say? The business major makes on average $8,000 more than the psych major. So I've related business to psychology, but I didn't say what psychology makes. Then we've got the English major makes $3,000 more than the psych. So I also related the English to the psych. Nowhere do I say what the psych makes. So the thing that you have absolutely no idea what they make, what they are, what it is, what it ought to be, that's the thing that you should call X. So we were not told anything about the psychology major, so I'm going to say that they make X dollars per year. However, the business major, we were told something. We were told that they make on average $8,000 more than the psych major. So that would be whatever the psych makes plus $8,000. More than means add. The psych makes X, so that's X plus. Come on, stop that. There we go. English major, we said, makes $3,000 more than the psych major. So the psych major again makes X, which would be a lowercase x, please. So the English major is going to be making X plus 3,000. You might say, well, Mr. Beckner, could I write 8,000 plus X? Could I write 3,000 plus X? Yep, absolutely. You sure can. That wouldn't be a problem. You're just going to see the same thing here. Ignore what you just saw. So that's us identifying the knowns and the unknowns. What do we know? What do we don't know? We don't know the psych major, but we do know the business related to the psych. We do know the English related to the psych. So these are our knowns and unknowns. Sometimes one of these will just be a number. Maybe I said the English major makes 40,000, and then that would just be a 40,000, and these would be X's and stuff like that. Write an equation out in words. The sum of these three majors averages is $116,000. So in other words, if I take the psych plus the business plus the English, $116,000. So there's our equation in words. That's us using our words. Then place your knowns and unknowns into the equation. So here is where people will make a mistake with this particular problem. they'll say, oh, okay, I've got an x plus 8,000 here, I've got an x plus 3,000 here, and equals 116. This is wrong, this is wrong, this is wrong. They'll go x plus 8,000 plus x plus 3,000 equals 116,000. This is wrong. They'll see this x and think that's the psychology major. They'll see the x plus 8,000 and think it's the business. They'll see this x plus 3,000 and think it's the English. They think they've got all three here, but in reality, they're missing the psychology major. They are double playing this x. They're double dropping this x. This is the biggest mistake I see in this problem. So take your time with this. So the psychology major is this x. Then plus, I don't need to change colors. The business major is the x plus 8,000. Then plus, the English major is the x plus 3,000. The business is this guy. The English is this guy. And the psychology major is this guy. And then we have equal to our 116K. Now, are some of you capable of going straight to this equation without doing any of the previous stuff? Yeah, probably. Am I going to give you full credit on a test as long as you get the answers right? Yeah. I'd still want to see some work, because if you make mistakes, how do you get partial credit? By showing your work. The more work you show, the more partial credit you might get. Trust me, most of you need to show more work for word problems than you think. All right, then what do? We solve the equation via the methods from 1.2. They're like terms, x plus x plus x, 1 plus 1 plus 1 is 3, so that's 3x. 8,000 plus 3,000 is going to give us 11,000. So 3x plus 11,000 equals 116,000. Then we're going to move the 11,000. We're going to subtract 11K on both sides, which will give us 3x is equal to 16 minus 11 is going to be 5, so that's 105,000. 3 times x, so we divide both sides by 3. We get x equals 3 will go into 10 3 times with a remainder of 1. 3 will go into 15 5 times, and then the rest are zeros. So x equals 35,000. Now you might say, oh, we're done, move on. Not really. You got x, but x isn't even always a solution. We were supposed to identify each major's individual average. These are not well labeled. What the heck is x? Well, x was the psychology major. So the psychology major makes $35,000 per year on average. What about the business? Well, the business is whatever the x was plus 8,000, x being 35,000. So it's 35K plus 8K, which would be 43,000. And then the English was the x plus 3,000, so that's 35,000 plus 3,000. That's a terrible looking plus sign. And 35 plus 3 is 38. So that would be our 3 answers. And you better make sure you have them in the right spots in my math lab, or very annoyingly, it would be wrong. Now on a test, if you had work and you emailed me and said, Mr. Beckner, check out question number 3, I just have the answers in the wrong boxes, am I going to give you most of your credit? Absolutely. I mean, it's a 5-point question. I'd probably take 1 point off for not paying attention to putting the answer in the right box. Be careful. Show your work. Take your time. Breathe. And do well. Now, a cool thing is here, you might have said, I don't want to write the 8,000 and 3,000, 116,000. I'm just going to write 8, 3, and 116. You can actually get the right answer that way as long as you know that your x would then be in thousands. So if I cut off the zeros here, I'm not going to show all the work, but if you just wrote x plus 8 plus x plus 3 plus 116, what you would get is that x equals 35, x equals 35, but then you'd have to remember that your x was in thousands, and you would still get the same 3 answers. So you can't shortcut things with bigger numbers sometimes like that. But if you don't trust yourself with it, then don't do it. That's up to you. Let's just show this. We've only got a few minutes left, so we're down here. I don't want to. The next example we'll do starting at the top of next class will involve what we call a linear fixed cost model. So a linear cost model says that a total cost is the sum of a variable cost and a fixed cost. You have a variable amount, which means an amount that changes, and a fixed amount that doesn't change. So this is kind of like with your home or your apartment or wherever, your house, your apartment, condo. You have your rent or your mortgage, which is fixed. It doesn't change every month. And then you have your bills based on electricity and water and cable and all that stuff that do change every month. Your electric bill is different every month unless you go on that payment plan. Your water bill is different every month. So there's vary. The word variable means it changes. So let's say in January, your rent is $1,000 and your electric bill is $300 because it's super cold and you have electric heat pump. That means in January, your total bill is, let's just ignore water, water's free. You'd be paying $1,300, the 1,000 plus 300. But then in February, let's say it's not as cold, you only pay a $200 electric bill, 1,000 plus 200 would be 1,200. So that rent stayed the same, but your electric bill changed. Now, we wouldn't be giving you dynamic values for different months. We would be giving you a variable amount, like let's say it's, I don't know, 300x minus, this is going to be terrible, 100, but only for the first 2 months of the year. It wouldn't be so specific for the problems we do. But then X would be January for 1, February would be 2, and it would work. Actually, that wouldn't work. Say January is 0 and February is 1. Terrible model for you, but I'm just trying to do something on the fly. So your variable amount is going to be something like 5x or negative 7x or 12x or 1/2x. The fixed amount will just be a constant. The fixed amount is going to be a number. The variable amount can change, so it needs a variable like a 5x or a 12x or something. Let's say you own a factory and you're making CDs and your factory has rent, that's constant. And then the cost to make your CDs would depend on, well, how many CDs you make, because the more CDs you make, the more CDs you have to buy. So if CDs are 10 cents each, in order to make 1 CD, you pay 10 cents. In order to make 10 CDs, you pay $1. So your variable cost there would be 0.1x. Say 10 cents, 0.1 times x, the number of CDs you make. This is a very typical type of problem for quantitative reasoning students, for pre-calculus students. And we'll see an example or two of it next time. But for now, I'm just going to leave you with those details. If you dig through your textbook and basically want to see the next example we do, it's going to have to do with a cell phone plan, one of them having a $20 fee and the other having a $5 fee. So we'll be doing that example next time. For now, we're going to go ahead and sign off. Remember that 1.2, finish 1.2, so that's due on Tuesday, January 25th. Remember, it's always 11:59 p.m. I'm not going to keep writing that each class. Always due by 11:59 p.m. the following Tuesday or Thursday. Now, even if for some reason we miss class on this Thursday because of snow, the homework has been assigned, that's a non-issue. If the snow comes early and we do miss class on Thursday, then you just get a day off. I'm not going to say a day off. I might say I need to put up this lecture on YouTube ahead of time using old recorded material due to the fact that we really can't fall behind in here. It is insanely tough. You probably think I'm already going fast enough. Imagine that we have to make up a day because I have to get to a certain point in the material to say this class is done. So it is much better if I just put it up on YouTube and say, watch it on your own time, most of us should have power, hopefully. And if not, watch it once you get your power back. Stay safe and all that jazz. Hopefully we don't have snow. But you just never know. I'm just popping this up real quick for someone that sent a PM. That's all we had. All right, so have a good day. Hopefully we see you Thursday. Hopefully we see you next Tuesday. Hopefully we don't miss any classes the whole time. And take care.